All right, I'm going to start by saying that this is a very technical video. You probably don't need to watch it unless you're specifically interested in the Meanwell UHP-1500 high voltage series power supply. These are brand new. Meanwell just started selling them. They're in quantity, they're $300-400 a piece, but they're 1500 watt variable voltage, variable current, user configurable voltage and current, which is really nice. They've got power OK, and they also have an enable signal. We'll kind of talk about all those in a little more detail. But their data sheet is severely lacking in detail, which is kind of annoying. And I've actually sent them a couple of emails, and I've tried to get in touch with them. They're pretty technical email questions, and this one I have like 13 questions. And Meanwell just has not been responding well, or honestly at all. They haven't replied to this one. I've sent it 3 times over the last 4 weeks. No response. It's amazing. But anyway, it is a really good supply, but I'm just kind of having to figure out a lot of the stuff on my own. It is an isolated output. For my testing, I am actually just hooking up to ground so that the HVDC negative here is earth referenced. You don't need to do that. It'll run floating as well, which is how I'm using it in the application I'm using it for. I have purchased quite a few of them, like $22,000 worth of them at this point. So I'm a little frustrated. I know I'm very small fish for what I'm doing, but anyway, I wanted to show some of the stuff I figured out on it. And that way, I'm going to name this video, Meanwell UHP-1500-HV or whatever, and hopefully that makes it searchable. But anyway, yeah, so the biggest question I have is, and I've been able to answer here, is how do you do the voltage and the current? So this has, the current makes a lot of sense. The voltage, I was confused because there's both a potentiometer you can turn, but then there's also an external control. And so my question was, how do those work with each other? And so when you have nothing connected right now, these are just disconnected and floating here, then the potentiometer controls the output voltage. And so this is the output voltage. And if you rotate it clockwise, you can go, this is the 230 volt model, and that's just the nominal output. You can set it from 165 to, I believe, 265 volts. Yeah, that sounds about right. And so, yeah, you can basically set this to whatever voltage you want. This is, CVCC output supply, so you can control both of them. So my first question was, what do these pins here, they basically have a header on the back here, and one of them controls voltage. I've added a label there so I can read it. And the other one controls current. So my first question was, well, is this just using a resistor divider? If I turn this pot, am I going to see the voltage change here? And the answer to that is no, actually. This circuit, when you don't drive it, is actually just sitting here at 0 volts. Both the voltage and the current one, the behavior is the same. It's just whether or not you're controlling voltage or current. Behavior is mostly the same. We'll look into that a little bit in a sec. So the next question then is, well, if I drive my own external voltage into it, is that in parallel to this voltage? And the answer there is also no. As soon as you start driving an external voltage in here, then the voltage is entirely controlled, and I'm going to show you that here. I'm just hooking this top DMM here is because the resolution on this old busted instrument is not very good. So I just use an external meter to measure the voltage. Make sure I have this right. Yep, okay. So you can see that as soon as we start driving this external voltage, I'm driving 1.4 volts right now. I'm getting down to 127 volts. That's about as low as you can go. Yeah, 123 or whatever. And that's actually what this is. This is rated to 50% of its nominal, and its nominal is 230, so 120 is that. I'm going to hop over to the data sheet here. You can see, I'm going to have to make this a lot bigger. Output voltage, let's see, voltage programming mode. You can see that when there's 0 to 0.4 volts applied, you might be able to see that. Let me zoom in one more. When there's 0 to 0.4 volts applied, then the output voltage is just 100%. But that's not actually true, so kind of confusing. So if you apply 0 volts externally, it really just uses the voltage you set here. So that's kind of confusing. So for example, I can very easily apply 0 volts by just shorting these out, and you'll see that the voltage is not 100% of nominal. The nominal voltage is 230. So it's kind of weird. This graph does not make a lot of sense. Again, when you have 0 volts applied, when you're in the 0 to 0.4 volt range, it's actually using the potentiometer. So this graph really should say from 0 to 0.4 volts, it's potentiometer derived voltage. So that's incorrect there. And so anyway, if you now come in here and are applying the external voltage again, you can see that once again, so we're now hooking up our external supply to the control circuit here. Oh, one thing I didn't point out, this control circuitry is not isolated. So it is the output voltage. So again, right now I have it ground reference, but if this is floating, then you need to make sure that your analog control circuitry here is also, you know, floating or not. It has to be referenced to the V negative here on your HVDC bus. It's a very annoying feature. I don't know why they didn't, you know, most power supplies just have, you know, an output pin. You know, if you look at something like this other Meanwell, and pretty much all other power supplies I've ever worked with, here's the Meanwell HLG480H, for example. The control on this here is, it's like a 10 volt signal, and you can either PWM it, so it's a 0 to 10 volt signal. If you leave it floating, it'll just be 10 volts, and you can PWM it, and if you PWM it at 50%, then you'll get 50% of the output current or whatever. But this doesn't have any of that, actually. The output circuitry on this does not have a pull-up. You have to provide your entire external power supply, which is kind of annoying. It's a very easy circuit. I've kind of drawn just a conceptual one up right here. See if I can get it to focus. So basically, if you take your HVDC positive bus, you throw it through a resistor here. I don't really know it, maybe 10K. I haven't played around with that. It doesn't matter. I mean, you need to be able to maintain this 5 volt Zener voltage. So if you put like 100K there, and then this voltage is collapsing when you're doing stuff, then you need to lower the resistance. So that's an implementation specific thing. And then basically once you get this, you know, this LM, you know, Zener reference or whatever, then you can have a potentiometer here that actually plugs into these voltage or current controls. And you could use the same Zener and have 2 different outputs. So if you wanted to have a potentiometer where you adjust the voltage and the current, for example. And then, yeah, you basically just do the non-isolated voltage reference here. You could put a capacitor on the output of this if you were trying to, and you should put one here too to keep it stable. But you know, you could have a capacitor out here if you want to do a PWM control. Again, though, not isolated. So you would need some opto-isolator or something, you know. If you're watching this video, that's going to be pretty trivial, I think. So yeah, now that we have this external voltage applied, I wanted to point out a couple of things. One, the potentiometer no longer does anything. So I can now adjust the output voltage by just adjusting here. And you can see that as I go up here, you know, say to 2 volts, I'm now at 150 volts. They really stress that this is a non-linear output. It looks pretty linear to me, but you know, whatever. I imagine they just don't want to specify a tolerance on its output there. Anything you're doing here, any kind of control circuit, you would be measuring this voltage. So who cares if it's nonlinear? It looks pretty linear to me. It's certainly continuous. There aren't any odd jumps or whatever. They don't specify the maximum voltage. On the graph, they show 5 volts. And at 5 volts, I am getting the maximum output voltage, which is 265 volts on this supply. I think it's actually only rated to 260, but it's a little bit nicer. Don't know what the upper end is. Probably 5.7 volts, who knows. You would probably want to Zener limit that if you didn't have control, a guaranteed control over that voltage. So one thing I wanted to point out is now that we're stable here at whatever voltage this is, 181 volts, potentiometer does nothing. So as soon as you get above the 0.4 volts or whatever, or probably the 1 volt there, potentiometer stops working. So that's good to know. They work mutually exclusively. So some outcomes from this. One, the output voltage range does not go to 0, which you already know. They specify that. That's not surprising to me, but you know, just so you know, you can only go from 50% to 120% of the nominal output voltage. Fine. The current is the same. Graph's a little different. There's no potentiometer for the current, but you can see that the output current is actually, and this is super annoying. This is frustrating. If you don't hook anything up to this and generate this output circuit here that I showed previously, there we go. If you don't have something like this controlling the current wire, which is just this wire right here, then the actual output current is 110% of the nominal rated value, which is kind of annoying because the power supply at 110%, it's not rated to work continuously there. So if you just take this out of the box and plug it in, and you're actually sourcing 110% of the current on here, this supply will output it until it overheats. Kind of annoying. Again, they say this is nonlinear. It's certainly continuous at least, and it seems pretty linear. It might have some bowed inflection, you know, a little oxbow one way or the other, whatever. Again, anything you were doing should be monitoring the current as well. Yeah, so basically, if you want this to actually output 100% of the current, you need to get a 4.7 volt Zener diode. They've probably picked the 4.7 volts so that you can just have a Zener on there. Again, they give zero guidance on that in here, so I find that annoying. But yeah, I don't like this external control circuit. I love that it is a CVCC because the other supply I showed, and most of these supplies are like constant current supplies where you don't really control the voltage other than as a function of the current. So it's neat that they've added the voltage functionality here, but it's not very well done. I could see someone making a small little attachment PCB here to basically generate, you know, 2 copies of this circuit I keep showing or whatever, and then maybe have some pots or USB, you know, opto isolators so you can set it. I mean, this could be a really nice supply. You know, it has power enable, so you know, you can't go down to 0 volts, but you could basically have a turn it on or off, and when it's off, it's 0 volts. When it's on, it's a minimum of, on this one, 120 or whatever, a maximum of 260. I think it was 120, whatever, it doesn't matter. So that could be neat. I mean, the power density on this is pretty insane. 1500 watts in this package is pretty impressive. But yeah, this control circuit was a bit odd. So that is one question, and I won't spend as much time on all of them, I'm sure. Let's see, I don't know where this email went. I need to find it. Hold on. We're gonna just, there it is another screen. So yeah, the second point here, this is actually, there's some oddities here. They basically say right here that you need to limit the output power to 900 watts max when your input voltage is 120 volts. So the boilerplate, the nameplate here, page 1 says that this is a 1500 watt supply, but it's only a 1500 watt supply at 240 volts or 180 volts or whatever, not 120 volts like what you would find in the US outlets here. The way I'm using this, my customers can either plug into 120 or 240, and you need to be able to limit the current or the power actually. And they say here, they say 900 watts max for inputs from 100 to 120 volts. But this supply doesn't actually limit it. So if you put 120 volts into this supply, it'll still output 1300 watts. It doesn't go out to 1500 watts then, but it'll do 12 or 1300. And of course, they're saying limit it to 900 here. Now, elsewhere in the data sheet, they actually give a different value, which I'm going to try and find. Let's see, limited. Okay, yeah. So in the data sheet, the static characteristics graph shows that when operating at 100 volts, the output power is limited to 67%, which is 1000 watts. And then, so there's basically a discrepancy. If you look at the graph in the data sheet, it says 1000 watts. And if you look here on the actual nameplate, it says 900 watts max. And again, this does not regulate it. So I've been able to pull 1300 watts at 120 volts in, which is above the spec. So again, it might cause it to overheat. Now, granted, I've done that for like 5 or 6 hours and it has continued working. This does have some overtemp sensors, particularly on the bridge rectifier here at the beginning. There's a temp sensor, you can't really see it here, but I've been inside of these a little bit. I actually make some mods inside of them, which is annoying because they're potted and you have to remove some of the potting, but that's irrelevant. Temp sensor on this input rectifier, this is the part that gets the warmest. So when you're running at lower input voltage, the current through this input rectifier is higher. So at 120 volts, it's nominally twice the current. This thing gets pretty hot. It has a temperature sensor bolted directly to it. So when it does get too hot, the power supply will turn off, and then when it cools down, it will turn back on. There's some hysteresis there. But the supply itself is not limiting the current. So it means that when you're actually building a product, you need to actually be able to measure the input voltage, and not if the voltage is applied, you need to actually measure it. So you can do, with a couple bits of digital isolation, you can determine if you're like less than 160 or greater than 160 volts, and then you can just say like, if it's less than 160, it's 120 volt input. If it's greater than 160, it's 240 volt input. But that requires external circuitry, which is just kind of annoying. It'd be kind of nice if on some of the unused pins there are I believe there's like 14 control pins here. It'd be neat if they could have a, what's the input voltage that's, 5 volt TTL. So you can just plug that isolated signal in. It doesn't have this, by the way. I'm just saying it'd be a neat feature if you could tell what the voltage is. Of course, a neater feature would be if this supply would actually just limit the input voltage by itself automatically. I'm sorry, the output current, or the output power rather, if it's at 120 volts. So if it has those limitations, why not just, it's got it here, it can measure if it's there. So that's kind of annoying too, because it gets really, really freaking hot. In my case, I am both doing a fan to cool this and a plate to cool this. So if you look in the guide, they basically show, you can do 100% of the rated power with either a fan or a plate. And I'm doing a fan that's slightly lower than they recommend, and I'm doing a plate that's quite a bit thinner than they recommend. But anyway, I've run this, I've tested it for hours and hours and hours, probably 20 hours over 4 sessions, and it's hasn't overheated. Kind of annoying. I wish that feature was built in there. So let's see. Oh yeah, there's some things where they just don't define units on their graphs, which is always annoying because you have no idea what they're graphing. Yeah, 3 we've talked about. 3B, okay. Okay, yeah, so this input rectifier, of course, is getting hot, I mentioned. Let's see, yeah, 110%, we talked about that. If you don't hook up this current pin, then it outputs up to 110% of the rated current, which is annoying. I run this at full current. If it is on, it's going full current. So it does get hot. Yeah, we talked about the nonlinearity. They call this potentiometer the SVR potentiometer. I still haven't figured out what that is. I posited that it means selectable voltage resistor. No idea what it actually means, but they use it everywhere. I hate when they have 3-letter acronyms, but they don't ever define them. Yeah, we've answered that. Okay, yeah, so I've already discussed this here, but this was confusing again. So the PV and PC, the voltage and current control signals here, I was curious, and again, we've already talked about it. The note in there says PV, PC functions when users do not use SVR, which is like, what does that mean? And then they also say, in addition to the adjustment via the built-in potentiometer, the output voltage can be trimmed. So that would, the first comment is saying basically that they work mutually exclusively, which is actually the behavior. The second one is kind of implying that they work in parallel. But anyway, yeah, so basically as soon as you get above a volt, this takes over. That doesn't matter at all. So I observed there's a capacitor right here inside that's not glued. So this whole thing is potted really well. It's rated to 5G. It's rated pretty well. But then there's a capacitor here, pretty large, electrolytic capacitor that's just, it comes off a daughter board PCB and then turns, and it's just loose there. So in mine, because I'm already opening them up to make other mods, I'm actually gluing that down because I don't want it to rattle and break. What else? Yeah, so it has this remote on-off. So it has a remote on-off and a power good signal. Those are actually both isolated, and those are 5-volt control. And actually, they're not 5-volt. The power good is a 5-volt TTL logic signal. The remote on-off one is not. The remote on-off one says, you short it out, then it turns on, and if it's left floating, it turns off. But when they say short it out, they really mean tying it up to plus 12-volt aux. So this has a built-in auxiliary rail. And so you actually have to tie the pin up to plus 12, which means if you're using a microcontroller, you're probably using an open drain FET or a transistor or whatever. But the good thing is that is already an isolated signal, so you don't need an opto-isolator on that, which is nice. The DCOK is 0 to 5 volts, though, so that's nice. But they actually don't specify what the isolation voltage is rated for. So they don't, is it 3,000 volts DC? Is it 5,000 volts DC? No idea, because they don't specify it. Yes. Okay, also, this does support PM bus and CAN. And they say in the manual, that it's supported, and they give you the pinout, at least how to connect the signals. But then it says, for details, please refer to the function manual. No idea what that is, and again, I've emailed them, but I've not heard back. So anyway, that is basically using this unit here. It's a very sweet device, but definitely lacking. The whole data sheet's only like 5 pages long or something. So yeah, that is it. It's very neat. It's certainly very high energy density. This will fit in a 1U rack, which is pretty neat. I'm not using it for that, but I am actually putting it in a very space constrained location. So this here, basically, you can see that the solution I have, and this is just me hooking it up. You can see I've actually added a couple more control wires in here. I've got a triac inside of there, and over here I'm actually, this is a blocking diode because I'm actually using this on a shared bus, so I need to be able to block that. I wanted to make that a MOSFET so I could lower the the conduction, the RDS on or whatever. It's a diode drop. It's it's not a MOSFET, but I wanted the RDS on because it'd be a lot less power sinking into here. But it's a safety element too, and I don't want to have a logic controller in there that could malfunction. So in this case, at the 6-7 volts output this is rated for, I'm getting a 0.7 volt times 6, so I'm dropping 4 watts or whatever into here. That's fine. Just some notes on using it. I definitely looked at putting fans inside of here before I mounted this one here. It's kind of at an angle. It's not the recommended way. They recommend blowing air that direction. Couldn't do it in my application. So I've got both the plate here, and that plate actually connects to these angle irons, or really angle aluminum brackets, and then these actually bolt to another surface. So the heat dissipates a lot through just conduction here. And again, they don't even require an external fan. I have it in addition. I'm actually powering it off the 12-volt aux, which is really nice. I'm just using that supply to actually power it, so that's pretty nice. I don't need an external rail there. But yeah, it's a great device. It's just the documentation is bad, hence this video, which is 22 minutes, which is, yeah, what I expected, to be honest. Anyway, if you have questions on the UHP-1500-230, I'm not going to answer them for you unless I've already answered them here. My recommendation would be to contact Meanwell. They are not a sponsor of this video, and they have not replied to my emails, so anyway, got to figure it out yourself. As always, thanks for watching.